Ladies and gentlemen, welcome to this not podcast, this webinar for basic math and stuff. Now, the impetus behind this conversation is that often someone running my courses, I start teaching stuff and we start doing reliability stuff, and there are always some students who just don't know what some of the symbols mean and some of what basic math stuff means. And often those people sit relatively quietly in the background and are somewhat embarrassed to admit they don't know what those symbols actually are, or how they relate to reliability engineering. And you shouldn't be embarrassed about it at all, because it's essentially a language that you either get taught or you don't get taught. And it doesn't reflect how smart or dumb you are. It just reflects what your experience in life has been when it comes to this sort of stuff. So what we're going to talk about today is basic math and stuff. We're going to do it in a particular way, which hopefully works with everyone. Now, before we move on, Fred has shared the link to the workbook for today's conversation. So please feel free to download that workbook as we go. It's an editable PDF document, and we're going to follow along today. It's got spaces for you to write in notes as we go and answer questions. If we don't get time to answer all the questions today, feel free to put in the chat window or email to me separately after this webinar has finished with the answer you think is right. I'll tell you if you are. So one of the many issues we have in this scenario I'm talking about is that we have my good friend, the ponderous professor, who's one of the many enemies of reliability engineering, one who always needs to make things way more complicated than usual to get answers, so on and so forth. The person, if it's not as complicated as he or she makes it, he or she doesn't feel important. We all know this person. We know this person has been responsible for lots of mathematics and statistical courses in the past, but this little conversation today is going to be a diet version of this dude. We do need to go into some basic math and stuff, and that's not something anyone would do if they had a choice on a weekend. So we're going to try and make it as fun as possible, but at the same time, hopefully answer a couple of questions, which I know we routinely get. So we're going to start with answering this question: what is arithmetic? Now, arithmetic is a word a lot of people associate with math, and in a way it's used interchangeably. And that's not a bad scenario most of the time, or not a bad conclusion most of the time. So let's start very, very simply with what arithmetic is. Now, I know most of you are going to know most of what we're going to talk about today, but the reason I'm doing this is to make sure that the little tidbits of things you learn today are uniquely valuable. You might know everything you might know 90% of this conversation today, but that last 10% is going to hopefully really, really help you. And of course, there's going to be a small number of students or attendees or people reviewing this recorded lesson webinar again, and they will be seeing this from scratch. So we're all going to get something out of this conversation, even if a good chunk of it is going to be revision. So let's start with arithmetic. And the most basic place to start with arithmetic is the plus sign and this minus sign. And of course, we have more symbols than this when it comes to arithmetic. We have the multiplication sign and the division sign. Now, these different symbols have lots of different names. For example, when we say adding stuff together, we say 1 plus 1. It's another way of saying add or sum, or in some cases, aggregate, or we tally up all these numbers. The minus sign is sometimes called finding the difference or subtracting. Division, we have the other words like quotient, or if we have a fraction, 1 over something else is another way of saying 1 divided by something else. And obviously we have multiplication in the bottom left-hand corner, which is also referred to as finding the product or times. So 1 multiplied by 3 is another way of saying 1 times 3. And so we have these 4 basic symbols when it comes to arithmetic, and these are called binary operations. A binary operation is a rule for combining 2 values to create a new value. So for example, 5 plus 3 has a rule behind that symbol, which means we're able to work out the total number this represents is 8. The rule essentially is we take all the things on in front of that plus sign and we combine or add it to whatever the phrase you want to use to represent what you've just seen visually represented on the screen. We combine what's in the left with what's in the right, and we quantify what we get. In this case, it was 8. So 5 plus 3 is equal to 8. Then we have the minus sign. So for example, if we want to have 8 subtract or 8 minus 4, the rule behind this binary operation is essentially we move from the left-hand side, whatever's on the right-hand side, and whatever's left is 8 minus 4. In this case, it just happened to also be 4. And then there's the times binary operation, the multiplication binary operation. The rule is essentially if we have whatever's before the symbol and create a grid where whatever before the symbol represents the rows and whatever's after the symbol represents the columns, then the total number of things in that grid is equal to 20 in this case. And that's the rule for 4 multiplied by 5. And we've missed one. Let's come back to the very last symbol, which is divide. So 20 divide by 2. The rule behind the division binary operation is essentially we try and find even groups. In this case, we want to break 20 things down into 2 even groups and see what the size of each group is, which in this case is 10. And so binary operations, I dare say we're all across binary operations, but these are very important to really understand. Whenever you hear a term binary operation, it refers to a rule where we take 2 numbers to create a third number. Now, on the left-hand side of this chart, we have plus and multiply. And these 2 binary operations have this thing called the commutative property. Now, of course, when mathematicians and scientists and statisticians write textbooks, they don't try and find words that actually are easy to remember, and commutative is one of them. All commutative means is essentially it doesn't matter the order. So, for example, 1 plus 3 is equal to 3 plus 1. But for these ones over here, the order does matter. So 5 plus 3, we know, is also equal to 3 plus 5. And now you can see in another symbol, the equal sign. It essentially means that whatever is on one side of the equal sign is equivalent to whatever's on the other. We know 5 plus 3 is equal to 3 plus 5, in this case, the number is 8. And so this illustrates how the plus sign, or the binary operation, I should say, which is more adding stuff up, is commutative. The 5 can go first or the 3 can go first, it doesn't matter. But of course, the same cannot be said for minusing or subtracting, because 5 minus 3 does not equal to 3 minus 5. So the commutative property is a very complicated word used to describe scenarios where it doesn't matter the order in which you do stuff like this. So that's a very simple overview of some of the most basic binary operations that we use in mathematics and statistics and reliability engineering. And maybe you learned maybe a teeny tiny thing about what binary operations do, but I fully appreciate that most of us have a pretty good understanding of what plus, minus, subtract, and divide are all about. But if you now know that these are what we call binary operations, that is a good outcome. But one of the reasons we want to use these symbols, these plus signs, these minus signs, these equal signs, is because they actually replace words. We don't want to write words every single time. We don't want to write 5 plus 3 where we spell plus P-L-U-S. That's 4 letters as opposed to a single symbol, which is a plus sign. And when we're doing lots of math, that can be quite a big deal. And that can make it a lot easier to write equations faster and solve them. So we often want to reduce the number of times we write stuff, including down to once if we can. So the next thing we're going to talk about is this thing called the function. Now, in reliability engineering, the function is often a behavior, process, action, or task that a system is intended to do. It's a very physical definition of function. So, for example, one of the functions of a car or a vehicle is to essentially be able to move. It is one of the functions is to be able to not only move, but take people, passengers, and loads from point A to point B. That's a function which would essentially be part of a design brief you give to your design team. But when it comes to mathematics and statistics, a function is simply something that relates an input to an output. Now, this is one of those definitions which is really simple to read, but until you actually see it in practice, it's hard to visualize what a function represents. One of the ways we represent a function in mathematics and statistics is with this symbol here, this lowercase f, followed by this lowercase x in brackets. And the x is the input, and the x represents a variable number that can be different depending on the situation. And the idea is this f of x. We often say f of x, where f is a function and x refers to the input. F of x essentially summarizes some function which will give us an output based on this input. Now, we can't work out what this function is just by looking at f. It needs to be defined somewhere. So, for example, we might define the function f of x to be equal to x plus 2. So on the right-hand side, x plus 2 becomes what we call the output. So let's see this function in action. We can see that we have 3 function values for 3 different inputs. F of 0 is equal to 2, f of 1 is equal to 3, and f of 2 is equal to 4. So when this becomes very useful, if we have to, for whatever reason, use this function a lot on paper or in books or in code or whatever the case might be, we don't want to have to keep writing x plus 2 every single time. We can define it once and simply say f of 0 is equal to 2 whenever we find the input as 0. So this is an example of a function, a very simple function. A more complicated function could look something like this, 3 times x plus 2. Now, when functions get quite long, that's where having a single definition somewhere on your page saves a lot of time and ink or keystrokes, because then we only need to write this equation once, and every time we wanted to use f of 0, we just write f bracket 0 close bracket. But if we look at this function here, there is a little wrinkle we need to be aware of. We, as a rule, always multiply and divide before we add or subtract. So whenever you see an equation like this with a multiplication and a plus sign, we need to be aware that we are always going to multiply or divide regardless of where it appears in the order of the equation. That always gets done first. So in this case, 3 times the f of 2, where the input is 2, 3 times 2 plus 2. We multiply 3 times 2 first to get 6. And then we add 2 after we've done that to get 8. So that might seem trivial, but it's actually very important. And let's just say we want to add first, because for whatever reason, the function we're interested in is 3 multiplied by the input plus 2. So what we can do is introduce these brackets. And these brackets tell me and you and anybody else that the first thing we're going to do when we solve this equation is do all the stuff in the brackets first. So for example, f of 2 is equal to 3 times 2 plus 2. We add 2 plus 2 first to get 3 times 4, and that gives us 12. And you can see that that's different to the number we had on the previous function, which was 8. So getting the order right is very important. So if we want to do addition or subtraction first, all we need to do is put a bracket around it. Now, this is very important because we're using functions to describe real-world phenomena. For example, we might have a function which tells us what the volume of a cylinder is, or the mass of a particular system based on certain dimensions, etc., etc. And these functions need to be tailorable in order to make it relatively easy to get this right. But there's another thing we want to do, because we're all about simplification. If we write everything we had to do in words out, we would never stop writing equations in full. So we often simplify these equations by not bothering to include multiplication. What does that mean? Well, whenever we multiply, and we multiply a lot, we can simply just remove that multiplication sign. And we now, as a rule, know that whenever we see two numbers next to each other, if there's no multiplication sign, they are multiplied. It's one additional way of simplifying notation, because we see so many multiplication signs that we've introduced this additional rule where if there is no sign, we assume it means multiplication. So we're all about simplifying. We're all about making it easier for us to write these relationships in a way that works. So this is sort of what mathematics and arithmetic's all about. It's taking what would be very long words or sentences to describe what we're trying to do, and use symbols to as efficiently and as quickly as possible represent what we're trying to achieve. Do we have any questions so far on what might be a very simple conversation? Cool, because it's going to get a little bit more complicated. Sometimes we want to go the other way. What does that mean? Well, sometimes we are given an output. We start with this one over here. I'll go back one slide. So we have a function here, f of x is equal to y. Maybe we know what the value of y is. Maybe we know what the function is, but we might not know what x is. So we might want to go, oh, went back one too far. We might want to go from y back to x. Wow, what happens if we need to find the input? So what happens if you have the volume of a cylinder and you need to work out its radius, for example? Now, we might have the function which gives the volume of a cylinder based on its radius and obviously height as well. But what happens if we perhaps know what the height is, we know what the volume is, but we don't know what the radius is, and we need to go the other way when we use our volume function. So one way of doing that is to come up with this thing called the inverse function. And all the inverse function is essentially that first function, but it goes the other way. And we have this -1 sign in the top top right-hand corner of, the top -1 sign come after the f to represent that this is an inverse function. So if f of x is equal to x plus 2, and in this case, we're saying y represents the output, then the inverse function is simply f -1 of y is equal to y minus 2. So we know that if, for example, f of x equals, if f of 2 equals 4, because 2 plus 2 equals 4, then the inverse function of 4 is 2, because 4 minus 2 is equal to 2. We go back the way we came. So you might have seen this inverse function, and every single function has its own inverse function you need to work out. So instead of adding 2, we're going to subtract 2. Now, there are so many different inverse functions we need to go through in order to get there. But, so many different inverse functions. Each one is unique to its underlying function. So there's no universal way to come up with an inverse function. You need to deduce it from first principles based on looking at your initial function. So, for example, if f of x was x multiplied by 2, then the inverse function would be y divided by 2 to get back to x. But there are still some more things we can do to make things even simpler. And so we've been talking about symbols, we've been talking about multiplication signs and plus signs and function symbologies and things like that. But then we get to notation. Now, notation is a series or system of written symbols used to represent numbers, amounts, or elements in something such as mathematics. Now, mathematical notation is simply trying to simplify over and over and over and over again, because we want to use as little pen ink or as fewer keystrokes as possible to summarize what it is we're looking at. So, for example, let's just say we need to add lots of different numbers. In this case, 1.34 plus 2.58 plus 4.59 plus 10.09 plus 7.01 plus 8.13. Well, that is a bit of a mouthful and it takes a long time to write out. One way of simplifying this just a little bit is to use this symbol at the very start of this line down here. Now we have shortened that expression a little bit. We've replaced 5 plus signs with one of these symbols on the left-hand side. And that matters. That actually reduces a lot of time and effort, especially if we're adding lots and lots of numbers together. So this symbol over here looks a bit like an E, is actually the uppercase sigma, which is the 18th letter of the Greek alphabet. But we can make things even simpler still. So before we move on to the next slide, I want you to remember that every time you see this uppercase sigma, this weird E-looking letter, we are focused on adding things together. So let's make things simpler still. A lot of us are reliability engineers. So when I say that if we use X subscript 1 to represent the characteristic of something, it could be how long it takes for something to fail, or it could be the thickness of an oxide coating, or it could be the number of units shipped in a particular month, or anything that you want to represent. But the reason we have the 1 here is that, of course, we might have lots of systems. So if we focus on the duration until our system fails, and X subscript 1 represents how long it took for our first system to fail. Or if we're looking at the number of units shipped in a month, then X subscript 1 represents the number of units shipped in the first month. Or if we're looking at the thickness of an oxide coating, then X subscript 1 represents the thickness of our first oxide coating. So X subscript 2 would be the second characteristic of something. X subscript 3, X subscript 4, and so on. And so one simpler way of adding all these things together is to go back to our uppercase sigma and write it like this, which means we don't have to write lots of different plus signs. Or we can simplify it further and write it like this. Now, this might be looking a little bit confusing, but let's break it down. On the expression on the bottom, you can see we have the uppercase sigma, and on the right, we have X subscript I. Now, I represents an index. If we define I equals to 1, then that obviously becomes X1. If I equals 2, then X2. I equals 3, it becomes X3, so on and so forth. But then we have this weird thing down the bottom. We'll go back one, which is an upside down A. Now, in math, that upside down A means all values of. So what this expression at the bottom represents is we're going to summarize X subscript I for all values of I. And that's all values you have. So if you only have 12 values of X subscript I, then you're going to sum all those 12 together. If you have 20, you're going to sum 20. If you have 30, you're going to sum 30. So you sum every single X subscript I you have for every I value that exists. But if we want to add a certain number of Xi's together, we might then write this, where essentially we describe the X subscript I's we want to add. Now, this expression here means we're adding X subscript I from I starting to 1 all the way to I is equal to n. So if n is equal to 4, then we're adding X subscript I, X subscript 1 plus X subscript 2 plus X subscript 3, X subscript 4, x subscript 5, sorry, up to x subscript 4, got ahead of myself. And that will essentially give us the answer, which becomes so much simpler than this. And if you have lots of numbers, you can use Excel, which has its own formula to help you out. Now, I'm not going to go into Excel in a great detail in this conversation, but I will give you some formula to help you out. So, for example, if we want to sum x subscript 1, which is 12.4, and x subscript 2, which is 13.7, and x subscript 3, which is 15.1, then one way of looking at this is realizing that we have 3 values to sum. So in this case, n is equal to 3. And so we can write this particular expression. We want to sum all these things together with our Greek uppercase sigma, I equals 1 is on the bottom. We write 3 as at the top, write x subscript I, which means that we're adding the first 3 xi's, which in this case comes to 41.2. So that is the notation for adding lots of things. That's obviously very important. But of course, it's not the only operation we're interested in either. We do lots of things where we, for example, need to multiply lots of things together. And we use a different symbol to represent that. In this case, we use this uppercase pi, which is the 16th letter of the Greek alphabet. The lowercase pi is very well known to represent the ratio of the circumference of a circle to a diameter. So if we want to multiply x1, x2, x3, x4, then we can simply, instead of using the sigma, we can use a pi. So in the same way that pi can be, this expression, the summations can be simplified further, we can get down, we can write this notation at the bottom, which essentially means that we're going to multiply x subscript I for all values of I. So every xi we have a value for, we're going to multiply them together. But of course, if we only want to multiply the first few of these things together, we often want to do that. Then we can write I is equal to 1 at the bottom and then put n at the top. And that tells us we're going to multiply the first n things, which again is so much simpler than this. And in Excel, you have this formula here. And so if we were to go back to a problem where we want to multiply 3 things together, we can see straight away we have 3 things. So n is equal to 3. And that means if we wanted to use notation to represent what's going on, we can use our Greek uppercase pi, write 3 at the top, write x subscript I over there, multiply, which means that we're multiplying 1.5 by 3.8 by 2.7 to give us 15.39. But we can make it simpler still. So for example, if we are multiplying the same value 3 times, which instead of being xi, is actually what this means is because there's no subscript I on the right-hand side, even though there's I underneath the pi, it just actually means we're multiplying x by itself 3 times, where x in this case has the same value. And when we do this, we don't want to write a big uppercase Greek letter pi. We write this, the power, the exponent, x to the power of 3. So we want to multiply x by 3 times. When we say that we have raised our number to the, or variable to the power of 3, this means that we're able to simplify notation that much more. And this number at the top here, this superscript number is what we call the exponent. Now, the exponent, again, is a complicated word that mathematicians have come up with to try and sell their own text. Well, that's not true. There's been no historical interest in using simple terms to describe mathematical concepts. So the exponent refers to the number of times a number is multiplied by itself. And of course, we can go the other way. So for example, let's look at 4 multiplied by 4. Now we know the rule for multiplication is that we create a grid where 4 columns and 4 rows, and we count the number of things in that grid. Now we just went through how 4 multiplied by itself can be summarized by or represented with 4 to the power of 2, which is equal to 16. So 4 squared is equal to 16. That's just one of the rules. Another way of writing this is to say that 4 is equal to this weird looking symbol over here, all over 16. This weird looking symbol is called the radical or the radix. So it's not a tree hugging hippie or a terrorist or anything like that. This is this symbol is called the radical or the radix, and in this case, it represents this thing we call the square root. And the reason why it represents a square root is because we had to create a square with sides and a width of 4 to create 16. So therefore, 4 is a number we need to create a square with 16 inside of it, 16 inside of it, 16 things inside that square. And so we use this term root, add it to square to say essentially that 4 is the square root of 16. So we know that x is equal to the square root of x squared. That is a little introduction to this thing called arithmetic. So before I move on, are there any questions? Any questions about arithmetic at all? It's just a bunch of rules and symbols and notation. Okay, so that's arithmetic. Some of you might have heard of this other word that also starts with A called algebra. Now, a lot of people think algebra and arithmetic are the same thing. They're not, but they are very similar. Now, algebra is like arithmetic. It uses the same 4 operations, binary operations. But the thing that makes algebra special is that it involves an unknown number, which we replace with a symbol. So for example, 2 plus 3 equals 5. We know this because this is the rule behind the addition sign in arithmetic. Now, we could say that instead of writing 2 plus 3 equals 5, which is essentially exemplifies a rule, we could write 2 plus 3 equals x. And the challenge for us is to now find out what the value of x is. The top is arithmetic, the bottom is algebra. We call x our unknown. Now, this might look a little bit too trivial, and it is a little too easy. So let's look at algebra in a slightly more complex scenario. Let's just say that we have, for whatever reason, derived this equation where 3 times an unknown value is equal to 12 minus that unknown value minus 3. This is what we call an equation. An equation is an expression where we have an equal sign in the middle because it equates whatever's on the left-hand side with whatever's on the right-hand side. And because the left-hand side is the same as the right-hand side, if we do the same thing to each side, we still get a same value. So what does that mean? Let's look at this equation and divide both sides by 12. Now, you might not know why I'm doing this, but for those who don't know why I'm doing this, just hold on and hopefully you'll see. Well, if we divide both sides by 12, we now don't have 12 x minus 3s on the right-hand side. We only have 1 x minus 3. And 3 divided by 12 is equal to 0.25. So now we divided each side by 12 to get 0.25 times x is equal to x minus 3. So now let's subtract 0.25 x's from both sides. When we do this, we get 0 on the left-hand side. Instead of having 1x on the right-hand side, we now only have 0.75 x's. Now we add 3 to both sides. When we do that, we get 3 is equal to 0.75x. Now we can divide both sides by 0.75, and 3 divided by 0.75 is 4, and 0.75x divided by 0.75 is simply a single x. And so this last step is called solving for the unknown. So that's what algebra is. It's a lot like arithmetic, but we have this symbol x, which usually represents something we don't know. Some value we don't know what it is, and algebra is all about rearranging and manipulating and having fun with that equation to find out what that value of x is. Now, if you weren't already bored, let's take things up a notch. Let's look at this thing called a matrix. Oh my goodness, now we're getting really, really into some very boring topics, because the definition of a matrix is a rectangular array of numbers. So not very exciting, I know. But matrices, which is the plural of matrix, are actually very, very useful. So here is an example matrix. Matrix can be any size. In this case, it's 1 in the top left-hand corner, 3 in the top right-hand corner, -2 in the bottom left-hand corner, and 4 in the bottom right-hand corner. So this matrix is 2 by 2, 2 rows by 2 columns. Now, this might represent, for example, coordinates of a ship at sea, or the speed of a certain thing moving through space, where each different number represents relative velocity in a certain direction. Who knows? But we can sometimes need to add matrices together. So, for example, if we add 2 matrices together, all we do is to create the third matrix. The outcome of this binary operation is we take each element, we call it, and for each corresponding element, we add them together. So 3 plus -3 is equal to 0, -2 plus 1 is equal to -1, and 4 plus 2 is equal to 6. So when we add 2 matrices together, the deal is they have to be the same size. If they're not the same size, you can't do it. So that's introduction to matrices number 1. Now, you might think that, I'm on top of this matrix stuff. So if we multiply 2 matrices together, well, we just simply do the same thing, but instead of adding, we multiply. Well, of course, that is not the case, because we need to make math way more complicated. I'm being facetious here, because what we're going to do now is quite useful in many scenarios. But instead of multiplying these different elements, we look at rows and columns. So the first matrix is all about rows, and the second matrix is all about columns. So when we multiply matrices together, we focus on the first row of the first matrix and the first column of the second matrix, and we then multiply the corresponding elements. So you'll see that the first element in the row and the first element in the columns is 1 and 4 respectively. So we multiply 1 and 4, and then we add that to the second elements multiplied by each other, which is in this case 3 by 1. And so when we multiply these elements together and add them up, we get 7. And that number is the number that goes into our final matrix. So let's now move to the bottom row, but the left-hand column. We then multiply -2 and 4, the first 2 elements, multiply 4 and 1, the second 2 elements, to get, in this case, -4. And that becomes the bottom left-hand element. And we do the same for the top row and the right-hand column. 1 times -3 plus 3 times 2 is equal to 3. So that gives us our top right-hand element. And our bottom row in the first matrix, -2 by -3 plus 4 times 2, is equal, in this case, equal to 14. And that's how we multiply matrices. Now, we're not going to go into why we do this, but that's very, very useful. And of course, if you ever need to do this, it's in the guidebook. So matrices, they are ways of storing numbers, and it can be very useful to do this for many reasons. But adding matrices is very different to multiplying matrices. So before we go on, are there any questions? Because your brain may be experiencing whatever this symbol here represents. Any questions? Still got a good chunk of the people who are here at the start. So I know that we are, oh, thank you, Kevin, not so far. All right, so some of you might be feeling what this symbol represents, but this symbol actually has a mathematical meaning as well. In this case, we don't mean that we use this exclamation mark or exclamation point to represent a scenario where we don't, it doesn't represent anything where we go, wow. This actually has a rule behind it too. We call this symbol here the factorial. The factorial is a product of all integers equal, less than or equal to a number. So for example, n factorial is equal to 1 times 2 times 3 times every single integer up until n. What is an integer? An integer is a whole number. So you can see 1, 2, and 3 are all integers. So this is useful for working out how many ways you can pick out items from a bunch of them. So let's just say we're very hungry, and some of us are. I'm always hungry. So let's just say I have 3 pieces of fruit, and I'm going to eat all of them, but I'm going to select them in a particular order. I have 3 choices for my very first fruit. I can choose an apple, a banana, or an orange. So I'm going to, in this case, I'm going to choose a banana first. So that's choice number 1. Now I only have 2 choices. So I can choose between an apple and an orange. So in this case, I'll choose an apple. And for my very last choice, well, I don't really have a choice. I only have one option. So here is the way I selected my 3 pieces of fruit. So how many different ways can I select these 3 pieces of fruit? Well, if we do a chart to represent what I just did, the first choice involved 3 options. So we had, you can see that the first fork on the left-hand side has 3 branches. The second choice involved two options. So even though there's 3 forks, they each have 2 branches, one under the number 2. And the last choice involved 1 option. So the fork actually only has 1 branch. So we actually have 3 times 2 times 1 ways of selecting our fruit, or 3 factorial. So factorials, this little exclamation mark, is really useful when we need to select things from a bunch of different things. But of course, we need to make it even more challenging, because let's just say we have 10 different pieces of fruit, but we're only going to select 3. Well, then we use this equation here to work out how many different ways I can select fruit. And in that case, it'd be 10. And if I was selecting 3 pieces of fruit, it would be, I'd substitute k equals to 3 into my equation, and it'd be n by n minus 1 all the way down to n minus k. So that's how we can calculate how many ways we can select things. But of course, this is a very long expression. So this little expression here is summarized by this fraction here, n divided by n minus k, and factorial, which is equal to this, not equal to, but we use this letter P, superscript n, subscript k, to represent the total number of possible permutations of k distinct objects from a total of n distinct objects. Now, the key word here is this thing called permutations, which is the order of things. The order of things matter. So if I was interested in recording which piece of fruit I selected first, which was a banana, and which piece of fruit I selected second, which was the apple, and which piece of fruit I selected third, which is the orange, then that, by definition, is a permutation. A combination is essentially the same thing as a permutation, but we don't care what the order was. So for the 3 fruit problem, or 3 fruit scenario, where I wanted to work out how many permutations there were for selecting fruit, banana, apple, and oranges was permutation number 1, banana, orange, and apple, permutation number 2, all the way down to our 6th and final permutation, there is actually only 1 combination if we don't care about the order. So if there's only one combination for, in this case, 6 permutations. So sometimes we're interested in permutations, sometimes we're interested in combinations. And the symbol we use to represent how many different combinations exist for k distinct objects pulled from n distinct objects is this one here, the combination function, sometimes written with these big brackets, n on the top and k underneath. So in this case, n factorial over n minus k factorial multiplied by k factorial. I know we're getting a little bit complicated here, but if you, at the very least, hopefully in the future, if you hear combinations, you can flick back to this guidebook, look at this equation here, and work out how you can calculate, or how you can estimate how many different combinations, possible combinations there are if you're selecting a certain number of things from a certain number of other things. How are we going so far, team? Are there any more questions? Still the same number of people at the start, or roughly the same. Okay, we're doing well, team. Hopefully, I dare say most of you know most of this stuff, but maybe there's 1 or 2 little things that you've learned which is going to help you in your reliability engineering career moving forward. So what we're going to talk about now, we're going to talk about guns. That might have surprised you, but we're not going to talk about guns per se. We're going to use guns as a tool to express how things are not always as neat and nice as what we've looked at so far. What I mean by that, let's just say that you're playing a game called Russian roulette. Now, Russian roulette is a game which I advise you not play. It means you can see that this is a revolver which has it has a capacity of 6 rounds in its chamber, in its revolving chamber. You can see that one of these chambers, or one of the possible holes in this chamber, this revolving chamber, has a round in it. The idea with Russian roulette is you spin the revolver so that there's a 1 in 6 chance that there's going to be a bullet if you pull the trigger, put the gun up to your head and pull said trigger. Of course, there's a 1 in 6 chance that the bullet will fire, which means that you, from using a reliability term, you probably won't fail. If you play Russian roulette, you probably won't fail. You probably won't get a bullet in the chamber that's going to be hit by the firing pin and discharge that round at great speed into your head. So obviously, if you're probably not going to fail, you should pull the trigger. Yes? Well, of course, no. The problem is that many cases, in many reliability scenarios, we have to deal with decisions where we essentially have to convince people, 5 out of 6 mathematicians seem Russian roulette as safe. Like that quote, thanks, Kevin. But we have to deal with scenarios where we say, hey, the thing's probably not going to fail within the warranty period. And the manager might say, that's great, so we can launch. And the answer is no, because even if 1 out of 10 things fail in the warranty period, that can sometimes be too many things. That can lead to bankruptcy if that destroys your profit margin. If you have a profit margin of 5% for whatever reason, because that's what the market suggests that you need to have, then if you have a warranty failure probability of 10, 15, 20%, which still means most systems or products are still going to be working at the end of that warranty period, you're almost certainly going to be going bankrupt, especially if you're a small startup company. Plenty of startups who have come up with great ideas, great new things, create products that probably are going to get through the warranty period, but the 20 and 30% that don't, which is very, very high when we're talking about warranty failure probabilities, destroy the profitability of that company. Now, I've just realized that we've got a few things that are probably not going to be able to finish in this webinar. I've obviously misjudged the content in terms of time so greatly that I just will not be able to get through all the stuff. However, the workbook covers all the stuff that we're going to be I would have talked about, starting with this thing like that we're about to examine in greater detail now. And that's where we use the word probably or probability. We use the scenarios where we can't say with absolute certainty what's going to happen, and we need to make judgments based on what will probably happen. But before we talk about this scenario where we play Russian roulette, there's a reason why people like arithmetic and algebra, and that is because arithmetic and algebra are essentially processes. We have rules, we take inputs and convert them into outputs. Now, algebra and arithmetic are both processes where we take an input, gets chugged through the wheels, and the rules that we have embedded within arithmetic and algebra give us an output. 1 + 2 = 3, for example. We love it. Humans love certainty. Problem with the real world, though, is processes are often random, just like our scenario where we're playing Russian roulette. And even if we have the same inputs, when I have a random process, we have multiple possible outputs. So the fundamental difference between arithmetic and algebra and the real world is that the real world is inherently random. And that's not often, that might not seem intuitive, because we live in a very deterministic age where we believe that if we could understand the world around us down to the atomic level, we can, in theory, be able to predict exactly what's going to happen in the future. And in theory, you absolutely can, because we know, have a pretty good idea about quantum mechanics and all those different forces, subatomic forces, et cetera, But in the real world, when you are designing, for example, a brand new internal combustion engine, you do not have the capability to model the location of every single atom, every single molecule in that engine. You don't have the ability to know exactly what the makeup of the lubricants will be when those lubricants are used to replace the oil of that internal combustion engine. You don't have the ability to know exactly how your users or customers are going to throttle up or throttle down that internal combustion engine, and those different profiles will have different effects on how that engine fails. So from one perspective, you could say theoretically, if we were able to know exactly every single factor that drives our process, know exactly where each atom starts, know exactly how our customer is going to use it, know exactly the makeup of each lubricant that gets put in, et cetera, we should be able to predict exactly how that machine is going to work and then also fail. The problem with that is it's just not practical. So we often have to look at the world as if we have single inputs. And that means that if we have two engines which are manufactured in the same company, in the same production line, when they sit next to each other, they look from our human perspective to be identical, even though we know they have their own unique range of defects and different slight variations and torques on the bolts, et cetera, even though we know that those things exist within these engines, or internal combustion engines, we cannot possibly we cannot do anything but, from a human perspective, treat them as identical. If you know that they're not identical, but don't know how they differ, then I'm sorry, when it comes to real world decision making, they're identical. If you don't know how they differ, you treat them as if they're identical. So random processes involve what seemingly identical scenarios which lead to different outputs. And now these outputs we often call events. Now, an event is a set of outcomes of a process to which a probability is assigned. So what can these events be? Anything you want them to be, whatever you define success to be, a hazard to be, consequence to be, a failure to be. Every time we have a probability, every time we have a random process of different outcomes, then if we can assign a probability to each event, even if we don't know what that probability is, even hypothetically do that one day if we were to analyze the process well enough, then we are dealing with events. But I've used this term probability quite a bit. What is probability? It's a measure of the likeliness or likelihood that a certain event will occur. Now, we are all about simplification. We're all about keeping things simple. So, for example, if we label an event as event A, then we can write the probability of event A occurring using this notation here: PR bracket A close bracket. Whenever you see this represents essentially the sentence, the probability of event A occurring. And that sentence you can see is on the top right-hand side of the screen right now. That's quite a long sentence if we have to write that out a lot. It's a lot simpler to write PR, open bracket, A, close bracket. So PRA is the probability that event A occurs. Now, if PR of A equals 1, that means event A will certainly occur. If ever we have a probability of 1, it means essentially it's no longer random. We know that event A is actually going to occur. So even though we're talking probability, it's actually a certain fact that event A is going to occur. We know the sun will come up tomorrow. Probability of A is equal to 0 means event A will never occur. So that is one way of understanding probability. 0 represents something that will never occur, and 1 represents something that will certainly occur. And sometimes you see some textbooks simplify things further and remove the R from probability and just use P. So when it comes to reliability engineering, we often deal with what we call the probability of S, or success, the probability that your product works. So R, which is often used to summarize or represent reliability, is equal to the probability of success. But we need to make sure things are very confusing, because life is confusing. So let's go back to some more confusing topics, even if you weren't thinking this is confusing enough. You might have heard of this thing called the Venn diagram. Now, the Venn diagram shows all possible logical relations between a finite collection of different sets. And oh my goodness, this is one of those definitions, which when you read it, you go, that's really nice, but what does that mean? Well, let's break it down. Some of you know what a Venn diagram is, some of you might not. But a Venn diagram is actually really simple. Now, a set is either an event or a bunch of events. And that can be, for example, if it's going to, you might say a set of bad weather events could include rain or wind or tornadoes. So that's a set of bad weather events. So when we look at sets and events, it's very important to understand that sets represent one or more events. So let's look at a Venn diagram. A Venn diagram usually starts with a rectangle that we represent the sample space. This rectangle represents all the possible different things that could happen from your random process. So for example, this could represent the fact that your system has component A somewhere in it. Or event A could be some smaller subset of these possible outcomes, such as event A or component A not working. Now, of course, it wouldn't be a discussion on probability and statistics if we didn't use a dice or a die. So let's just say we're looking at the process of rolling a dice. What is the sample space of rolling a dice? Well, we know that if we roll a dice as a cube, which for all intents and purposes will randomly land on one of these sides, we know that this will give us an outcome of 1, 2, 3, 4, 5, or 6 being on the upmost side. So in this case, what we do to represent that scenario is represent the random variable with an uppercase X. So we'd essentially use uppercase letters to represent the random variable in terms of words. So if we define X to be the number rolled on the dice, then we can use this weirdy looking shape over here to essentially say that our random variable X, we don't know what the value will be, but we know it's going to be an element of 1, 2, 3, 4, 5, or 6. So if we go back to our Venn diagram, let's just say that we actually have a scenario where our system has two components, components A and components B. And we use these circles to represent events where component A isn't working and component B is not working. Now you can see that these events overlap, which essentially means that it's possible, or these circles overlap, I should say. So it's possible for both A to not work and B to not work. But if, let's just say that we are interested in finding out when component A or B doesn't work, then we're interested in the outline of those two events, and we call this brand new event a union event. It's based on an OR process. It's a union event because we have unified events A and B, and we represent this union event with this this cup shape over here. Now, this is very important if you have, for example, a series system. Now, if we have a series system with two components, A or B, that means that our system will fail if A fails or B fails. So this big union event represents our system failing if we have a series system. So let's go back to our original Venn diagram. Let's just say now, let's focus on scenarios we're interested in events where both A and B don't work at the same time. It's not a union event anymore. This is what we call an intersection event based on the keyword and. We use this symbol over here on the right-hand side. Now, this is very, very useful if we have scenarios where we like for example, a parallel system where the system will only fail when component A fails and the backup or redundant component B fails. So that's why this probability stuff, this discussion we started with Russian roulette, is important to reliability engineering. Now, this Venn diagram is a very useful way of visualizing how probability can affect or ruin our day. So if this event here, or this circle here, represents event A, which is in this case component A not working, then whatever's left in our sample space is component A working. You can see that we have this symbol on the left-hand side, A with a line on the top. So inside the circle, it represents a component A not working. Outside the circle, it represents component A working or being functional. So this event A dash with this line on the top is what we call a complement event. It complements A. It's sometimes referred to a not event, so not A. And so these these three relationships are the bedrock of probability and statistics. On the left-hand side, we have the complement, and on the right-hand side, we have binary operations in the probability space. Now, because I've grossly underestimated my ability to get this content to you within an hour, I am going to have to regrettably stop right there. But that said, in the guidebook, there is continuing discussion, continuing exercises and explanations on additional things which are based on the Venn diagram concepts we just went through, where we looked at intersection events, union events. You'll talk about, the guidebook talks about these things called mutually exclusive sets or mutually exclusive events, statistically independent events, rare events, conditional probabilities, and of course, random variables. Now, of course, if you have any questions on what is left in the guidebook, which I regrettably can't get through in today's conversation, don't know how I got this timing way out. Probably should have broken it down into 2 webinars in hindsight, Fred. Apologies in advance. But feel free to reach out and ask any questions of anything I write in those guidebooks, or any questions about probability in greater detail, or probability, arithmetic, or algebra, because they're not that complex or complicated scenario concepts. It's all about just using symbols to represent the real world stuff around us. And that means that we that if you don't understand these seemingly complicated hieroglyphics in a course or a textbook, doesn't mean you're an idiot. It just means you haven't learned that language. You haven't experienced what it takes to get on top of these symbols. And often we are sometimes bashful or shy when it comes to admitting what we do or don't know, especially in reliability. And hopefully today's conversation has given you at least one little factor which will make your life at least a little bit easier moving forward. So on that note, are there any questions before we call it a day? No questions whatsoever? Or has everyone fallen into a coma or a catatonic state with all these numbers and stuff? Oh, Kevin says it's like no question, but thanks for your feedback. Thank you, Mahendra. Refresher is a term I'm expecting a lot of you guys. Enlightening, good Lord. Thank you, Joseph. I'm glad that you saw it that way. And of course, a lot of this is boring, but hey, if we can get to the bottom of some of these symbols, it just makes our life that much easier. And of course, makes us all sound smarter, which is the main point of what these conversations are all about, walking away, trying to sound smart to other people. Okay. Right. Okay, so part two would be something I'll talk with Fred about that. Matthew said that he missed the first 5 minutes. Which handbook are you referencing? Fred's just put the link to said handbook in the chat window, Matthew. Thank you, Michael. All right, you have my contact details, or should be able to find my contact details for Ascendo team. Thank you very much for your time, Fred. I think we're good for today.